Welcome back to this channel. So in this video we are proceeding with the sixth video under ionic equilibria. So in this video we are going to be looking at acid-base titrations. So this video is specifically made to explain all titration graphs that are involved in chemical or ionic equilibria. Now at the end of this video, you must be able to plot and also explain graphs under ionic chemistry or ionic equilibria as of U.A.C.E examinations. With acid-base titrations, which is the main topic that we are going to be elaborating specifically in this video. Now here we are saying that acid-base titration is going to be the addition of a solution of a base to that of an acid until there is just enough of the acid to neutralize the base. So in other words, this can be a neutralization reactions. Acid-base titrations are the ones that you carry out in your laboratories, and they are made purposely to find the end point or the neutralization point where the acid has completely neutralized the base. It's the acid that is being added to the base. Now let's proceed with acid-base indicators, and here we are saying that an acid-base indicator is going to be that substance which is going to change color according to the hydrogen ion concentration of the solution or liquid in which it's being added. So whenever you are being asked for the definition of an indicator, it's going to be that substance which only depends on the concentration of hydrogen ions in the solution for it to change its color. Now going to the action of the indicator, seeing how it functions. Now functions of an indicator. Indicators are represented by this symbol, HIN. And we are saying that the action of an indicator is going to depend on the concentration of hydrogen ions that are present in each and every solution. So considering phenolphthalein indicator, which is commonly used in our laboratories, we are saying that phenolphthalein indicator is going to be a weak acid, hence partially ionizes. So we are going to be explaining in terms of equilibrium. In terms of chemical equilibria, this is going to be like concentration. If this concentration exceeds if more of the hydrogen ions exist, the equilibrium reverses. And if more of this exists, the equilibrium also reverses. So you make sure that you are very good at chemical equilibria before you proceed with ionic equilibria. So HIN, or phenolphthalein indicator, partial ionizes, which is represented by partial arrows, to form hydrogen ions and IN ions in aqueous solution. Now we are saying that here the unionized HIN ions are going to be colorless. That means that if more of this exists, the solution is mainly colorless. And if at all the anions of IN, I'm going to call them the in ions. If at all the in ions are existing in excess, the solution is going to be pink. So take note that if you're having excess of HIN ions or excess of this in the solution is going to be mainly colorless. And if you're having excess of this, the solution is going to be mainly pink. So let's see what happens. I've told you this is going to be explained in terms of chemical equilibria as we explain the factor of concentration. We are going to see when you add the base, how does it affect? How does it affect the concentration of the ions or our unionized indicator? So we are going to be looking at the components that we add. How do they affect these components here in this equation? Because our indicators are weak acids and are weak bases. So let's look at the explanations. Indicators are only weak acids. You don't have any indicator which is a base. So you're saying that here, looking at the explanation, when an acid is added to the indicator solution, the hydrogen ion concentration in the equilibrium, take note, I've told you that you're going to be explaining according to equilibrium. If you add an acid to this solution here, the hydrogen ion concentration in equilibrium is going to increase, and therefore excess hydrogen ions are going to be present. And under chemical equilibria, we say that if concentration of the products is increased, equilibrium will have to be reversed. So more of these are going to react with this to form back the unionized HIN molecules or the unionized phenolphthalein indicator molecules. And we say that if more of this exists, then the solution is going to be mainly colorless. So repeating this, if we add an acid, the hydrogen ion concentration increases, and when it increases, excess of the hydrogen ions are going to react with the in ions in order to restore equilibrium, so that we can form unionized HIN molecules. Now we are saying that here, equilibrium is going to be shifting from right to the left, because that's where the reaction that is being favored is occurring, maintaining the value of the ionization constant Ka to be constant. And then we are saying that here the solution is going to become colorless. It's becoming colorless because we have excess of the HIN molecules, and it says that if you're having excess of the HIN molecules, the solution is going to be mainly colorless, and if you're having excess of the IN molecules, the solution is going to be mainly pink. So adding an acid reacts with the IN molecules, excess of them react with the IN molecules to form back our unionized HIN molecules. If we add the base to that solution, so when a base is added to that solution or to the indicator solution, the hydroxide ions are going to react with the hydrogen ions. Remember that hydrogen ions are going to be coming from the ionization of the HIN molecules. So that means that we shall be reducing the concentration of hydrogen ions in solution. Now to restore equilibrium, more of this has to ionize to form back the hydrogen ions that are being taken away by the hydroxide from the base. So adding the hydroxide reacts with the hydrogen ions that are present in equilibrium. Now equilibrium is going to be disturbed. Equilibrium is going to shift to the right. From the left to the right, more of the HIN molecules is going to ionize to form more of the hydrogen ions to restore equilibrium. So that means that we shall have less of HIN molecules and more of the IN molecules, because more of this HIN is ionizing, and that means that the solution is going to exist as pink. So hydrogen ions, which are present from the partial ionization of our indicator, react with the hydroxyl ions, which are from our base, forming water, everything in aqueous. Now we are saying that here, more of the indicator ionizes, just like I've explained, shifting equilibrium to the right, and therefore a relatively large concentration of in ions is going to be produced, maintaining the value of the ionization constant, or maintaining the value of Kc or Ka constant, and are saying that here the solution becomes pink because we're having excess of in ions in solution. Now let's look at the action of methyl indicator. Now they're all represented by the same symbol, HIN. So for methyl indicator also, it's a weak acid. It partially ionizes to give hydrogen ions and in ions in solution. Now you're saying that here, if at all we are having excess of unionized HIN molecules, our solution is going to be predominantly red. And if at all we are having excess of the in molecules when you're using the methyl indicator, our solution is going to be yellow, just like you do them in your practicals. Now we are saying that here, when an acid is added to the indicator solution, the hydrogen ion concentration is going to increase, and therefore the excess hydrogen ions are going to react with IN ions to form back the unionized HIN molecules. Now in this case, that means that HIN molecules are going to exist in excess, and when they exist in excess, our solution is going to be predominantly red, and that's how these indicators work. So shifting equilibrium to the left. So if at all we have excess hydrogen ions, to restore back equilibrium, this reaction has to be reversed. So equilibrium has to shift to the left, and therefore more of this will react with this to form back this, meaning that you are going to have excess of HIN molecules in solution. And therefore, if you have excess HIN molecules when you are using methyl orange indicator, we end up with our solution becoming red as the predominant color seen in the solution, maintaining the value of ionization constant, and therefore the solution becomes red. So we write an equation showing that excess of hydrogen ions react with IN ions to restore back equilibrium by forming back the unionized HIN molecules, so that to keep equilibrium constant, or to keep ionization constant. And since we are going to be having excess of this HIN molecules, that means that our solution is going to be predominantly red. So looking at the base, when a base is added to the indicator solution, the hydroxide ions are going to react with the hydrogen ions so that they can form water. So when a base is being added, a base is going to reduce the concentration of hydrogen ions. And just like in chemical equilibria, I say that once one of the products is reduced, the concentration is reduced, more of the reactant has to dissociate. But here it's going to be ionization. So more of the HIN ions ionize to form back more of the hydrogen ions that are being taken away by forming water using the hydroxide from the base that is being added. So when a base is added to the indicator solution, the hydroxide ions from the base, they come and react with hydrogen ions that are present from the partial ionization of our indicator, forming back water. Now this equilibrium is going to be disturbed. That means that more of the HIN molecules have to ionize. The more they ionize, the more they form back these hydrogen ions that were taken away. But remember that they are also going to be forming more of the IN molecules, or the IN molecules, or ions. So in ions in solution are going to become excess, and we say that when they're excess, our solution becomes predominantly yellow. The pH volume curves for acid and base titrations. Here we are going to be looking at the titration of a strong acid versus a strong base. Now in salt hydrolysis, notice that all these titration graphs, the steep part that you are going to be seeing is called the salt hydrolysis part. Most of you forget this. It's a very common mistake for people who are trying to attempt all these questions. Now from B to C, this is where the salt hydrolysis takes place. But when you're handling a topic of salt hydrolysis, we say that only salts made from strong base and a weak acid, or a weak base and a strong acid, undergo hydrolysis. And here, if at all you're having strong acid, strong base, salts do not undergo hydrolysis. That means that the pH you are most likely to have is going to be 7. So the pH that you're going to be seeing between the mid of the graphs is going to be at the end point where salt hydrolysis takes place. So let's look at sketch the graph, and let's look at the explanation. So the graph is pH against volume of sodium hydroxide that is being added in centimeters cubed. So the labeled points are going to be explained. We are going to explain initially why the pH is at A, and then we also explain the variation between curve AB. We also explain the variation between C, B, and C, and also explain the extent from C to D. For that, you're going to start with the explanation of the shape of the graph. Just like I said, we start with initially. So initially, pH is low. And why is it at low? Why is it low at A? This is due to high concentration of the hydrogen ions from complete ionization of the strong hydrochloric acid. Remember that we are dealing with a strong hydrochloric acid. Is what we are adding a base to it. And since you're having a strong acids fully ionize in solution. That means that they give off high concentration of hydrogen ions in solution. And once hydrogen ions are present in excess, pH is always very low, normally below 2. That's why our graph was at point A, which is initially below, or initially near 0, just slightly above 0, because HCl is a strong acid and it fully ionizes to form a high concentration of hydrogen ions in solution. Now going to that, we explain AB. So pH gradually increases along AB as sodium hydroxide solution is being added. And why is that the case? This is due to excess hydrogen ions still present, as some of the hydrogen ions are reacting with the hydroxide ions to be neutralized. So as we are adding little sodium hydroxide solution, you find that sodium hydroxide is going to be offering the hydroxide ions, but they are going to be present in few because we have only added a little volume of sodium hydroxide. So since hydrogen ions are present in excess, just a few molecules or a few molecules of the hydroxyl ions in solution are going to react with some of the excess hydrogen ions, neutralizing them to form water. So that's why pH is gradually increasing, because you are reducing the number or the concentration of hydrogen ions in solution. Remember that pH only depends on hydrogen ion concentration. So let's look at the pH We're also saying that pH sharply increasing along BC, and I've told you that these points of sharp increase in most of the graphs that we examine, they are going to be about salt hydrolysis or the end point being reached. That's a point whereby we are forming a salt, as we are going to be seeing the various explanations and examples. So we are saying that pH sharply increases along BC even with little addition of sodium hydroxide solution, and this is because all the acid has been completely neutralized. You either say because the endpoint has been reached, or you say that the acid has been completely neutralized and therefore the endpoint is being reached. All these points carry marks. So you're saying that here pH at the endpoint is 7, and the reason why pH at the endpoint is 7 is because sodium chloride, salt, that is being formed at the endpoint does not undergo hydrolysis. This word must be a must in your titration graphs. You must tell us whether the salt formed undergoes hydrolysis or it does not undergo hydrolysis. So you find that pH at the endpoint or at the neutralization point is just 7. And the reason for that, we looked at it when we are explaining salt hydrolysis. We say that salts that are made from strong acids and strong bases do not undergo hydrolysis. And if you have a solution whereby hydrolysis is not taking place, always pH is going to be neutral. So explaining along CD, we are saying that along CD, pH is going to be gradually increasing, and this is due to excess sodium hydroxide solution that is being added. So in excess of sodium hydroxide solution that is being added, remember that all the hydrogen ions at the endpoint are being neutralized. So if at all we are adding excess of sodium hydroxide, we are increasing hydroxide ion concentration, and you are completely reducing to the minimum the hydrogen ion concentration, which means that our pH is going to be gradually scaling up. pH is only low when the hydrogen ion concentration is increasing, or it only decreases when hydrogen ion concentration is increasing. But when hydrogen ion concentration is decreasing, pH is always leveling up. This is the same graph, but just tilted in such a way that the other time we are being adding sodium hydroxide. So in this case, we are going to be adding hydrochloric acid to sodium hydroxide. Now, since we're adding sodium hydroxide, pH is going to be generally higher because sodium hydroxide is a strong base, so it fully ionizes to form a lot of hydroxide ions in solution. So its pH is going to be near 14. Reason being it's a strong base, therefore it undergoes full ionization. So along AB, we are seeing pH gradually decreasing. Reason being, we are adding a little volume. We have added a little volume of HCl. And this HCl, what it has done, it has provided few of the hydrogen ions. So the few of the hydrogen ions react with the excess of some of the excess of the hydroxide ions that are present from sodium hydroxide, and therefore some of them being neutralized. So you find that the hydroxide ion concentration is decreasing. That's why the pH is gradually decreasing as we are adding in some hydrogen ion concentrations. So we find that BC, I've told you that these sharp decreases are always due to neutralization, and neutralization is because of the endpoint being reached. And at the endpoint, you must specify the pH which is there. You get it by getting a point in the middle. If you are plotting this graph, you note down the points here, and you also note down the points here, and then you add them, and then you divide them by 2. So if you are being told to draw a titration graph, and you have found this curve where your graph is simply plotting, let me say at B you are having 22.4, and then at C you are having 20. You have to add the 2 and then you divide them by 2. Just like the way you calculate average volume in your chemistry. So here you will be getting 42.4 divided by 2, and once you divide by 2, you're going to end up with 21.2. Now you find 21.2 in this curve. That's where you plot and find the pH at the endpoint from the y-axis. Always remember that, because you'll be drawing these graphs quite often. So the pH at the endpoint is going to be 7. And the reason for this, I've told you, the reason for this is going to be because of salt hydrolysis. You have to know whether the salt that you are forming is undergoing salt hydrolysis or not. So this is always now CD, the pH is steeply decreasing because all the hydroxyl ions are being neutralized, and therefore you're just increasing the concentration of hydrogen ions in solution. So let's look at the elaborative explanation. Of that graph, we are saying that pH is gradually higher at A because sodium hydroxide you're having complete ionizes forming many hydroxyl ions, and therefore we expect our pH to be slightly or very close to 14. Now we're also saying that here pH gradually decreases along AB. Now here this is not sodium hydroxide, it's HCl being added as we are adding our hydrochloric acid to sodium hydroxide, and this is due to excess of hydroxide ions that are present from the large volume that you are having of sodium hydroxide, and we are just adding a few. We are just adding a few of the acid or a very little volume of the hydrochloric acid, and therefore few protons of hydrogen ions from the less volume of hydrochloric acid being added react with some of the excess of the hydroxide ions present in that solution, and therefore they just neutralize a few. That's why pH gradually decreases. So few protons react with some of the excess of the hydroxide ions from the base, forming water, which is neutral, and our pH is going to be slightly higher. Now if you look at pH between B and C, is going to sharply decrease, and the reason for that, even with the addition of hydrochloric acid, and the reason for that is because that's the point. The sharp decrease or sharp increase is always going to be the point of complete neutralization, and at the point of complete neutralization is the point whereby we have the end point being reached. And after saying that, I say that you have to state the pH which is there, and you give a reason for it. So we are saying that here the pH at the end point is going to be 7, and the reason for it is because the salt, which is sodium chloride, being formed does not undergo hydrolysis, and the reason you gave for that is because sodium chloride is a salt that is made from a strong base and a strong acid. So if you look at a point along CD, pH is going to be gradually decreasing, and this is due to excess hydrochloric acid that is being added. As you are adding more, remember that at the end point you have neutralized all the hydroxide ions present. So as we are adding more of the hydrochloric acid, the protons are not going to be, the protons or hydrogen ions are just going to be in solution, and the more you increase hydrogen ions in solution, the more it decrease pH. So that's why pH is gradually decreasing from C to D. It's always due to excess additive or reagent that is being added, which is always on your x-axis. Titration, whereby we are going to be having a weak acid and a strong base. Now pay attention to these graphs, because these are the ones that are going to be commonly reflecting in your papers. And the reason why they are these ones is because for them they involve the aspect of buffer solutions. Remember that what we said about buffer solutions, as we said, we talked about an acidic buffer, and we said that an acidic buffer is going to be that solution whereby we are having a weak acid and its salt that is made from a strong base. And we say that that means that if you're having excess of the weak acid and we are forming a salt of that acid, we are going to be having an acidic buffer. And you remember the explanations that we gave about them. You also talked about the basic buffer, and the basic buffer, we say that here for basic buffer we need a weak base and also its salt, which is made from a strong acid. So that means that if you look at these graphs here, if you're having excess of the weak acid and we add a little of the strong base, a strong base is going to react with some of the ions of the weak acid to form a salt of a weak acid, and therefore if you're having excess of the weak acid in solution and some of the salt which is formed from a strong base, we are going to be forming an acidic buffer. So take note of that. So here we are going to be titrating sodium hydroxide against ethanoic acid, and the graph is therefore going to be showing that we are going to be adding sodium hydroxide. So what do you notice here? That means that we are having excess of the weak acid here. And if you're having excess of the weak acid here, that means that initially initially when you are beginning, after adding in a small amount of sodium hydroxide, you are going to be having a weak acid being in excess, and also the salt which is formed from a strong base, which is sodium hydroxide that you are adding. So you are going to be having an acidic buffer initially when you are starting, because we assume that our weak acid is in excess, and at the beginning the sodium hydroxide that you are going to be adding is going to be forming a salt, and you are going to be having a weak acid together with its salt made from a strong base, which is a definition of an acidic buffer. And that's the importance of these graphs, and you should understand them properly because you'll be required to sketch them and also explain them. So let's look at some of the way we can explain them properly. So looking at the graphs, it's going to be pH, which is always again is volume, not always, but here we are going to be adding volume of sodium hydroxide, which is going to be measured in centimeters cubed. Now here we are saying that our pH is initially at point A. If you look at point A, it's very far away from 0. Reason being, we are dealing with the weak acids. So weak acids, we expect them to partially ionize in solution, giving off very few hydrogen ions in solution. Therefore, the hydrogen ion concentration is going to be low. Thus, pH is going to be slightly higher than that of 0 as compared to the previous graphs, which are around here, because for them they were for strong acids. Now, along AB, you are seeing that pH is gradually increasing. Remember that here we are adding a little of sodium hydroxide, and we are having excess of the weak acid, which is ethanoic acid. Now, if you add sodium hydroxide to ethanoic acid, you are going to be forming a sort of sodium ethanoate. But from A to B, remember that from this point to this point, we are having excess of the ethanoic acid. And if at all we are having excess of the ethanoic acid and we add a little volume of sodium hydroxide, we are going to be having excess of the ethanoic acid together with the salt that is being formed, which is sodium ethanoate. And the two form an acidic buffer. And you know what acidic buffers do? We say that acidic buffer solutions are going to be those solutions which are going to resist change in pH when small amounts of acids or bases are being added to them. So along point B to C, you are going to see that pH is going to be sharply increasing. And we say that at this point, you give 3 points. First of all, it's a region of complete neutralization. And then secondly, complete neutralization is because an end point is being reached. And then thirdly, or lastly, you explain the pH which is present at the end point. So you find here, pH of 7 is here, but our end point, if you add this point here, point B, and point C, and then you divide, you're going to find that the mid is here, the average is here, which is going to be your pH. So you're going to find that pH is going to be slightly above 7, because you assume that the salt that is being formed here undergoes what we call salt hydrolysis. And I told you, sodium ethanoate undergoes which hydrolysis, as we are going to be seeing. So along C to D, or the preceding graph is going to be due to excess amounts of the reagent that is being added, or the reagent that will be present on your x-axis. So let's look at the elaborative explanations. Explanation of our shape of the graph. Initially, just like I said, pH is relatively low at A, and this is due to relatively high concentration of the weak ethanoic acid. But someone else can say it's relatively low because ethanoic acid is a weak acid, therefore it partially ionizes, giving off less protons, hence there's going to be less hydrogen ion concentration in solution. Now, if you look at the gradual change that is taking along AB, we are going to say that here pH is gradually increasing. And why is that the case? As sodium hydroxide is being added, it's because the very few hydrogen ions that are neutralized by the hydroxide ions. First of all, as we're adding sodium hydroxide, some of the hydrogen ions from ethanoic acid are going to be neutralized by the hydroxide ions that are being released. But also, the unneutralized ethanoic acid and then the sodium ethanoate salt being formed, they constitute an acidic buffer solution, just like I've explained. So first of all, part of the hydroxide ions from sodium hydroxide are going to react with a few hydrogen ions neutralizing it. That's why pH starts on gradually increasing, because the hydrogen ion concentration present in the solution is being reduced by some of the hydroxide ions reacting with the hydrogen ions. But also remember that as they are reacting together, the sodium ions react with the ethanoic acid, forming sodium ethanoate. And remember that at the beginning of the experiment, we are having more of the weak acid ions present, or more of the unionized ethanoic acid molecules present. We have also formed its salt, which is sodium ethanoate. And the two, as we discussed earlier in buffer solution, the two constitute what we call a buffer solution. Now this buffer solution is the one which resists change in pH or resists increasing pH. So going to the point or explaining what the variation of pH along BC, we are going to say that pH is going to be sharply increasing. And he said that here there are 3 points. One of them is because of complete neutralization, and the other is because of the endpoint being reached. And to do that, we write an equation. Ethanoic acid reacting with sodium hydroxide that is being added. For complete neutralization, you form what we call sodium ethanoate and then water. But the sodium ethanoate salt formed, remember that the third point I told you about is talk about pH. So it's saying that here pH at the end point is going to be above 7, because the sodium ethanoate salt being formed undergoes what we call an ionic hydrolysis to form an alkaline solution. So sodium ethanoate, someone else can first ionize this so that you can remain with ethanoate ions only, and you cancel the sodium. So ethanoate ions react with water. Remember that ethanoate ions are conjugate bases, so they accept a proton from water. Now what water will do to form unionized ethanoic acid molecules? Remember that ethanoic acid molecules are already present. But here water is going to be forming excess of the hydroxide ions, which are not present. So the formation of these excess hydroxide ions, which are not present, is what pushes pH above 7. So an ionic hydrolysis releases, remember that when you're dealing with hydrolysis of weak things or any hydrolysis, we use partial arrows. So always remember that, because it may deny you mass. So the excess hydroxide ions released in solution are the ones responsible to make the resultant solution with a pH above 7. Now explaining the points beyond C or along CD, pH is gradually increasing because you are adding excess of sodium hydroxide solution, which is increasing the hydroxide ion concentration in solution, hence an increase in pH. To be looking at the same idea but just tilted graphs. The other time we are adding sodium hydroxide, this time we are going to be adding ethanoic acid. But remember here, a buffer is not going to be present at AB, because at AB we are having excess of sodium hydroxide. We shall be adding less of the acid, and for the buffer to be formed, we need more of the acid, which is going to be along CD. More of the acid, and then less of the salt being formed. So after the salt being formed, probably between B and C, and you're having excess of the acid, that means that the acidic buffer is going to be formed at this region. Always you have to be good at interpreting these graphs. And pH is going to be above 7, just because the salt that we form between B and C undergoes an ionic hydrolysis, releasing excess of the hydroxide ions in solution, responsible for making your solution alkaline. So let's dive into the explanation. Explanation of our shape of the graph, I say that it's going to be the same explanation, but it's just that we have altered the structure, we have altered the shape of what we are adding. So initially, our pH is very high at A because the sodium hydroxide is a strong base, and being strong base, it undergoes what we call full ionization or complete ionization, forming very many hydroxide ions in solution. Now the hydroxide ions formed in solution are the ones responsible to hike the pH to be near or close to 14, as we saw in our graph. So looking at the pH, we say that pH is going to gradually decrease along AB as ethanoic acid molecules are being added. And the reason for this, remember that ethanoic acid is a weak acid, so it partially ionizes to form very few hydrogen ions. Now since we are having excess of the hydroxide ions from sodium hydroxide, they are going to react with some of the hydrogen ions, forming what we call water, hence decreasing the concentration of hydroxide ions in solution, causing a gradual decrease in pH. Or we can say that due to excess of sodium hydroxide still present, as some of the hydroxide ions are being neutralized, just like I've explained, from the few hydrogen ions from this partial ionization of this acid being added. And then we look at the sharp decrease, and we say that at the sharp decrease we're having 3 points to explain. Now, first of all, is due to complete neutralization. Complete neutralization is occurring because of the endpoint that is being reached. Then you have to write the equation for the complete neutralization. So you say that ethanoic acid reacts with sodium hydroxide, forming sodium ethanoate and water. But remember that I told you that this salt is a strong salt, so it fully ionizes, forming ethanoate ions and sodium ions. Now the ethanoate ions formed, so we talk about the third thing is pH. We talk about pH. So pH at the end point is going to be slightly above 7. And the reason why it's slightly above 7 is because the sodium ethanoate salt formed undergoes what we call an ionic hydrolysis. So first of all, we split this, though I didn't do it here. We split it because it's a strong salt to get ethanoate ions and sodium ions. Now the ethanoate ions undergo an ionic hydrolysis with water and they accept protons from water, forming back our ethanoic acid. And then which was already present, that means that they don't affect, this one does not affect pH, but after water donating a proton, it forms excess of the hydroxyl ions which are not present. So the increase of the hydroxide ions in solution is the one which is responsible to hike pH above 7. So you're having a pH above 7 due to excess concentration of hydroxide ions in solution. And I told you that whenever you're dealing with hydrolysis, make sure that all the equations that you're writing are having reversible arrows. So along CD, our pH is gradually decreasing, and this is due to excess of ethanoic acid which is being added together with the sodium ethanoate salt that is being formed to form a buffer solution. So the gradual decrease, along CD is due to because we're having excess of the ethanoic acid, just like I explained in the graph. We're having now here excess of the ethanoic acid, and at the same time we're having the salt. So here we're having excess of the weak acid, and you're also having its salt, which is made from a strong base at the same time. Now the two constitute what we call an acidic buffer, and we describe buffers as solutions that resist change in pH when small amounts of acids or bases are added to them. So that's why pH is just gradually decreasing. So let's look at the titration of the graphs where we are going to have a strong acid and a weak base. And once again, a review. When you're having excess of the weak base and then we are having its salt which is made from a strong acid, we form what we call a basic buffer. Now notice that these questions are not only going to be asked for you in titration graphs, but you're also going to find them in mixed questions. And mixed questions are those questions that come in terms of explanations. Explain why the solution of this and this behaves this way. Or explain why the pH of such and such a solution behaves this way. So let's look at titration of ammonia solution against hydrochloric acid. And here you're going to find that our pH as compared to 7 is going to be below 7. And then our pH is going to start generally low because we are adding ammonia solution to HCl, and HCl is a strong acid. Therefore it fully ionizes to form a high amount of hydrogen ions in solution. So we expect the hydrogen ion concentration to be very high. That's why pH is very close to 0. And then from A to B, we are seeing that pH is gradually increasing because we are adding ammonia. As we are adding ammonia to HCl, we are forming ammonium chloride. So most of the HCl ions or the hydrogen ions from hydrochloric acid are being neutralized. And at the same time, we are forming the salt. So here along BC where we're having a sharp increase, we say that here we talk about 3 things. So first of all, you talk about complete neutralization. Secondly, you talk about endpoint being reached and you give an equation for it. And then lastly, you talk about the pH as compared to 7. Is it above or below? And then you give a reason for it. But the reason however is going to be attached to salt hydrolysis. And then along C to D, we also give a reason for it. Now along C to D, we are going to be having excess ammonia. Remember that this is ammonia. So we are going to be having excess ammonia together with the salt that is being formed on complete neutralization, which together they form what we call a basic buffer. And therefore pH is going to be increasing gradually. Let's look at the explanation of the shapes of our graph. Now initially, just like I've been explaining, pH is lat A, and this is due to high concentration of hydrogen ions from complete ionization of the strong hydrochloric acid. Now pH gradually increases along AB because ammonia solution being added reacts with hydrochloric acid and they get neutralized by forming a salt of ammonium chloride. Now remember that this salt is a strong salt, so it will fully ionize to form ammonium ions and chloride ions. The ammonium ions, since they are from a weak base, they are going to undergo what we call cationic hydrolysis. But I told you that is under the steep part, which is along PC. So along BC, pH is sharply increasing with the addition of ammonia solution, and this is because first is due to complete neutralization, and secondly is because the endpoint is being reached. And then also comparing pH with that of 7, you are going to find that our pH at the end point is below 7. And why is it below 7? Because the salt that we are forming, the ammonium chloride salt that we are forming, it fully ionizes in solution, forming ammonium ions. Now the ammonium ions formed undergo what we call cationic hydrolysis. And then whenever we undergo cationic hydrolysis, we form acidic solutions. Our resultant solution is always acidic because these cations, the ammonium ions, release protons to their conjugate acids. So they release protons to water, forming the hydroxonium ions or hydrated hydrogen ions, responsible to turn the resultant solution acidic. And then they form the ammonia molecules which are already present. So in turn, you find that the solution is going to be mainly acidic, and it's mainly acidic mainly because of cationic hydrolysis, or simply hydrolysis. So we explain along CD. Along CD, just like I explained, we are going to be having excess of the ammonia and also the salt which is being formed, which together they form what we call a basic buffer. So pH gradually increases due to excess ammonia solution added, which together with the ammonium chloride salt formed, they form what we call a buffer solution. Or you can be more basic and advanced by saying they form a basic buffer solution. Now the solution which is being formed, just like buffers do, resists changing or resists increase in pH. That's why the increase is gradual. Titration of hydrochloric acid against ammonia. Now this is the same graph, it's just that it's being inverted, just like we have been doing others. So initially, pH is slightly below 10. In fact, pH is very far from 14. Because ammonia, we consider it to be a weak base, so it partially ionizes to release very few hydroxide ions in solution. That's why pH is far way below 14. And it's also below 10. And then also, you are seeing a progressive decrease in AB. Remember that here at AB, we are having excess of our ammonia solution, and we are going to be adding a little volume of HCl. So the little HCl added, we form what we call ammonium chloride with our excess of ammonia. So now we are having an excess of a weak base, and we are having also our salt being formed of ammonium chloride, constituting what we call a basic buffer. So this one is gradually decreasing because of the basic buffer solution that we have formed that resists change in pH. So along BC, we say that always this one, we give 3 points. So we talk about complete neutralization. We also talk about endpoint being reached, and then the third point, we explain the pH at the endpoint. Is it below or above 7? If you look at this one, it's always below 7. So you have to explain why it's below 7, and the reason for that is going to always be coming from salt hydrolysis. So along C to D, we explain why the graph is gradually decreasing, and we find the reason for this is because we are adding hydrochloric acid, which is a very strong acid, and therefore it produces very high concentration of hydrogen ions in solution, responsible for the progressive decrease. Looking at the explanation of the shape of the graph, we are going to be saying that initially pH is slightly above 7 or at A, And this is because ammonia is a weak base, and ammonia being a weak base, it partially ionizes to form hydroxide ions, just like I explained. So you're going to find that very few hydroxide ions are present. That's why pH is far below 14. Now pH gradually decreases along AB as hydrochloric acid or as small amounts of hydrochloric acid are being added. And the reason for that is because we're having excess of ammonia in solution, and therefore together with the ammonium chloride solid being formed. Remember that the less volume of HCl being added reacts with some of the ammonia to form ammonium chloride. So you're having excess of ammonia and our salt of ammonium chloride salt. And therefore, we form what we call a basic buffer solution. And a basic buffer solution is going to resist the decrease in pH, or someone can simply say which resists the change in pH. So continuing, you're saying that also here, some of the ammonia solution is being neutralized by hydrochloric acid. So ammonia reacts with hydrochloric acid to form ammonium chloride at the same point. Now pH decreases sharply along BC, even with the addition of hydrochloric acid. First of all, is because the endpoint neutralization has happened and the endpoint is being reached. And pH at the endpoint is below 7, reason being the ammonium chloride salt formed first of all is a strong electrolyte, so it fully ionizes to form ammonium ions and chloride ions. And the ammonium ions formed, they undergo what we call cationic hydrolysis, or simply you can say hydrolysis to form an acidic solution. So here, the ammonium ion acts as a conjugate acid by donating a proton to water. And once it donates a proton to water, we form what we call ammonium molecules and then the hydroxonium molecules. Now, formation of the hydroxonium molecules is what causes the resultant solution to be acidic, hence the pH which is below 7. So looking at the points along CD, we are seeing that here pH is going to gradually decrease due to excess of the hydrochloric acid being added. The end of this video is concerned with titration and acid to base reactions under ionic chemistry. Now we are going to be meeting the other video where we are going to be dealing with solubility or equilibria, solubility and calculation of solubility product. So ensure that you subscribe to the channel, share the video to your friends, and make sure that you attend to the next video, which is the most important one under this branch. So solubility equilibria is going to be divided into two videos. One of them is going to be for explanation of the theory behind it, and the other one is going to be purely for calculations. So thank you for watching the video. See you in the next video.